So what we're doing today is spectroscopy, and spectroscopy measures the interaction between light and matter. And then there's subdivisions of this. There's gamma ray spectroscopy, X-ray spectroscopy, UV spectroscopy, visible spectroscopy. We're doing visible spectroscopy today because we're going to measure the interaction of visible light with matter. We have a little bit of UV and a little bit of IR, but what are the range of wavelengths for visible light that we're looking at? And so these you need to memorize. The edge of violet is at 390 nanometers, and the edge of red is at 760 nanometers. And so pretty much we're going to be looking between 390 and 760. But our spectrometers that we use to measure, actually this gets a little bit of infrared. And that little bit of infrared would be wavelengths greater than 760. And so for our spectrometer, we can go to 900 nanometers. This is nanometers. And so we get about 100 nanometers deep into IR. Is 100 nanometers deep into IR very deep? No. And so we call that near IR. It's near red. And so let's say up to 1,000. 1,000 nanometers would still be considered near IR. When you get to maybe 1,000, 2,000, 3,000 to about 10,000 nanometers, then we call that mid-IR. And wavelengths greater than 10,000 nanometers we call far IR. Okay, then microwaves have wavelengths. IR, 10,000 nanometers is 10 microns. And so IR has wavelengths on the micron level. Microwave has wavelengths on the centimeter level. Like microwave oven, I forgot the exact wavelength, but it's around 8 centimeters. It's the wavelength, 8 centimeters is pretty big, the wavelength, But it's moving so fast, the speed of light so fast, that the frequency of a microwave is 2.4 gigahertz. 2.4 gigahertz is 2.4 billion 8-centimeter wavelengths moving past you in 1 second, which is incredibly fast. But we're not going to worry about that. You should know visible. Visible ranges from about 400 to 800. And so if you had a wavelength of, let's say, 2,000 nanometers, where would you think that is?
Near.
You don't have to know near, mid, far. We'll just say it's in the IR. You aren't going to see it. Violet, the edge of violet's 390. Not everybody can see that far. But then we break into UV. And so if we had a wavelength of 250 nanometers, where are we? UV. We're in the near UV. They're the same thing. Near, far UV, depending on how close you are to violet. So if you're near, you're here. Far, you're there. So let's say I had a wavelength of 100 nanometers. UV. Right? Let's say I had a wavelength of 5 nanometers. You think I'm at X-rays? No. It's likely because what we see in terms of wavelength is orders of magnitude. Over here we have wavelengths that are like smaller than an atom. Over here, do you know how big the wavelengths get? Like some radio waves are meters or kilometers long. Like AM radio is a kilometer long. A kilometer, that's still a kilohertz. 1,000 of those kilometer wavelengths pass by in 1 second. It's huge. And so we're talking about huge orders of magnitude changes in terms of wavelength and frequency. And so here, 1,000 nanometers, a couple of thousand, 5,000, 10,000 should still be in the IR. And tens and single-digit nanometers here should still be in the UV. And so what spectroscopists do is they want to measure what frequencies of light or what wavelengths of light, wavelength and frequency, it depends on what type of spectroscopy you do. Some spectroscopy, like visible, always does wavelength. Other spectroscopy does frequency, but it doesn't really matter. You should know, though, these two wavelengths. Anyway, what we want to do is, what wavelengths of light interact with that matter? And we want to measure those. And so this is why we collected the data. We saw what wavelengths of light were emitted by the light bulb, measured that, all of them. What wavelengths of light were emitted by the hydrogen lamp? Not all of them. That kind of thing. And measure. When we measure it, there are two ways of measuring these. One is by exciting the electrons and seeing what colors of light are emitted. That's what we did in experiment 3. We did something called emission spectroscopy, where we generate emission spectra. Spectra is plural. Or if we just generate one of these, we call it a spectrum. Singular. And so if we look at the emission spectrum for white light bulb, and we're going backwards here, Roy G. Bibb, because we're going in terms of decreasing energy, increasing wavelength. If we look at the emission spectrum of the light bulb, was very much ultraviolet light emitted? Did you see much ultraviolet light emitted from this light bulb? No. Actually, you couldn't see much because we only went down to 380. We only had 10 nanometers in the UV. But what you saw is it went down to the baseline. When it goes down to the baseline, we're plotting intensity here. And so there's very little intensity of high energy violet and very little intensity of ultraviolet here, which is good because you don't want a lot of ultraviolet light coming from a light bulb. And then we had pretty good intensity of all the colors of the rainbow, including colors you can't see, which would be, actually these aren't colors, this would be the, what's beyond red, infrared. And so that light bulb was emitting some heat, some infrared radiation. You could feel it with your hand, but you just can't see it. It's infrared. So this is what we call a emission band, or continuous spectrum. Continuous spectrum. It's continuous because, do you see any forbidden? No. It's pretty much continuous from these limits here. And it's called an emission band. And so a band of frequencies, a band of wavelengths, a band of energies are allowed here. Continuous band of those. Whereas, if we looked at the spectrum for hydrogen, the spectrum for hydrogen wasn't a continuous band. The spectrum for hydrogen, this is for a light bulb, and so if we try to make a light bulb out of a hydrogen lamp, it wouldn't be so great. Because in the hydrogen lamp, we see some red light being emitted here. There's a pretty intense peak, call it a peak, and some green, and some blue, and a little bit of violet. It's hard to see. And so we get a very distinctive looking spectrum here. This is called a line spectrum. Line spectrum because only certain frequencies of light were emitted from this lamp. Red, green, blue, and violet. Not just any red, but a specific shade of red, a specific wavelength of red was emitted. And then the other lamps gave you their own unique spectrum. So this is characteristic. You can identify unknown elements based on their spectrum because this is the fingerprint of the element. And so some people do visual detection of this. Like, for example, they can tell that sodium might be present because sodium, when it's present in a flame, do you know what color the flame is? Yeah, orange, yellow, like that lamp. When there's potassium present, then, you know, these colors add up to give you kind of a brick or a violet color. I'm going to do a brick color, violet, etc. We'll look at some of those later. All right, the other type of spectroscopy is what we're doing today. The other type is called absorption spectroscopy, the opposite of emission. And so we're going to see what colors of light are absorbed, not emitted by the matter. Absorption spectroscopy. Absorption spectroscopy, we do this. If we're looking at the hydrogen atoms, H atoms, do they absorb all frequencies of light? No, it turns out that an electron has forbidden energies, or forbidden frequencies, or forbidden wavelengths, and allowed. And so if we look at the absorption, it looks pretty much like the emission, except the units are different. Here we have the absorption on the Y. And so if we shine, for example, if we shine indigo light on hydrogen, does the electron in hydrogen absorb that indigo light? No, it's forbidden. And so the absorption spectrum, it'll absorb some violet, it'll absorb some blue, absorb some green, and absorb some red. And the intensity of absorption is shown by the height here. So it looks just like that. Well, for absorption, what we do is we shine all the colors of the rainbow on it. And so we don't have to excite the sample. We don't have to heat it up. We don't have to put an electric current through there. All we do is shine white light onto it and see what colors of the rainbow are absorbed. And it turns out just these 4 colors here. Okay, this is a line spectrum. Again, line. Showing many. How about a black body? What would the absorption spectrum look like for a black body? A black object. It absorbs everything, all the colors. It absorbs, right? So it'll appear black. Well, it turns out, what about red food color? Do you think red food color absorbs everything? No. And so what does red food color absorb?
Everything except
All red.
All red?
Orange.
And some orange? Okay, let's take a look at red food color next. In other words, what makes red food color red? If red food color absorbed all colors, it would look black, or white, or colorless. You know? Actually, it wouldn't look white. White is not absorbing all colors. Do you know what white is? Reflecting all the colors, right? All right, so red food color looks red because it absorbs red? No. What you'd want is, you want to absorb everything except red. And so the absorption spectrum would look like this. All the colors are taken out except for red. And the red passes through, so the only color not absorbed, in other words, we're filtering out all the other colors of the rainbow and only allowing red to go through. If only red goes through, then that's what we're going to see, just red. But that's not the only way red can be made. You know, there are other ways red can be made. You know, there are many different shades of red. And so, let's say you have an LED TV. How do you make different shades of red? Do you just use the red LED? No, you don't use the red LED. You can mix in some blue and green to come up with different shades of red. And so what we do is we could do some color mixing. to generate red. And so the spectrum might look like this. The spectrum might be red, green, blue, and we mix different amounts. So we have a little bit of red here, some green, and maybe some blue, and they'll change the color. Actually, maybe it should be mostly red. Red, green, blue. Does it have to be red, green, blue? No. It could be, or somebody this morning said it should be blue, yellow, red. Maybe, blue, yellow, red. We mix different amounts of these to get a certain shade of red, right? Or, etc. And so this would be mixing. This would be kind of filtering out the other colors. Is there another way that red food color can be red? Yeah. There's another way. And that has to do with complementary colors. 3. We can absorb the complementary color and so to figure this out, we generate the color wheel. Red, orange, yellow, green, blue, indigo, violet will combine into one, because indigo and violet have kind of a narrow wavelength range. And so this is the color wheel here. So one way to make red is if we absorb the opposite here would be green. If we take out green, then these colors average out or combine to form red. And so take out green, these colors will add up to red. And so what would the spectrum look like? Well, the spectrum is going to look different here. The spectrum will, okay, I'm going to draw it like this. Roy, G, Biv, and indigo violet were combined like that. This should have a peak. We call it an absorption band or absorption peak at green. It's not a line. You would expect an absorption line. It should absorb just the perfect opposite of the shade of red you have. So maybe this shade or that shade. But the reason it's not a perfect line like this, a line spectrum, is because of vibrations. The vibrations of molecules will change the energy of the molecules a little bit, rotations as well. And so what we get is an absorption band, But it's not a continuous band, it's just a band around green here, absorption band. So we'd expect an absorption band about how many nanometers? So the visible ranges from about 400 to 800. We'll round up. 400 to 800, and green is kind of in the middle. Actually, just to the left of the middle, because indigo violet's kind of short. And so, right in the middle would be, between 400 and 800 would be 600. So maybe around 500 to 600, we would expect a peak here corresponding to the absorption of green light, resulting in a red color. And so those are 3 different ways that we can generate red in red food color. What we're going to do is, sure, it'd be great to theoretically predict this, right? But quantum's not so easy, right? The calculations. And so what we're going to do is we're just going to take some measurements using this spectrometer. And so let's go ahead and set this up. So I'll stop the recording here. a lot more clear.